All right, we're going to get started now talking about the implications of the linear perturbation pressure term associated with the rotating updraft, and specifically what happens when we're dealing with a curved hodograph, or one that is bowed out relative to what we talked about earlier, or compared to what we talked about earlier, we were dealing with a straight hodograph. So now let's draw a curved or bowed out hodograph over here, something like this. With height, we'll have a hodograph that arcs something like this, southerly flow that becomes more southwesterly. It's still southwesterly, but there's going to be some difference here based on this concavity that's apparent in the hodograph that is going to influence which of those flanking updrafts becomes dominant. And that's what we'll be talking about at this point. So let's think about this hodograph, and from a symmetry perspective, let's split it up to the west and east of this dashed line, effectively representing the maximum value of this parabola-looking curve over here. Let's look to the left of this particular curve over here. What we see is that partial u bar partial z is greater than 0. So we're going down shear, or just down the hodograph, and partial u bar partial z is greater than 0. And then we go farther to the right of that dashed line, and partial u bar partial z is still greater than 0. So we have a consistent sine shear profile, effectively, as we're going down shear in this particular case, where partial u bar partial z is not associated with any alternations, I should say, in its sign at all. It's effectively constant sine shear profile. And we know from what we showed previously that is going to be associated with down shear propagation of each of those updrafts, the flanking updrafts included in that. But what's different about this hodograph compared to what we talked about last time is that now we have an alternating shear profile associated with the mean meridional wind. From this point to this point, at every single chord along this hodograph over here, partial v bar partial z is going to be greater than 0. We have more meridional motion as we go to the right. Once we get to this maximum value in this parabolic function over here, partial v bar partial z beyond that point now becomes negative. We have less meridional flow as we get to the points to the right of this particular line over here. So previously, when we talked about the W prime, effectively the horizontal gradients in W prime effectively dictating where our new cell development and propagation was going to take place in the mid-levels, that was the only factor that we really had considered in terms of explaining where our perturbation pressure terms were to have a specific sign, particularly in mid-levels, because we dealt with a uniform sign of the vertical shear term corresponding to the zonal wind. But now, the vertical shear profile associated with the meridional wind is alternating. So that is going to play a more substantial role now in terms of explaining which of the propagation terms becomes dominant over here in explaining cell motion, because of the alternating sign of this vertical shear term associated with the meridional wind. So while this is still going on and we get downshear propagation, we're going to have to now incorporate differences in the perturbation pressure results over here associated with linear effects between the low levels and the high levels, because we have the alternating shear profile associated with this curved hodograph. That's what gives us the alternating shear profile. That's going to be what's going to give us differences in the perturbation pressure gradient force between the left of the shear vector, I should say left of the initial updraft versus the right of the initial updraft relative to the shear vector. And now I'll explain that visually over here so it's more clear. All right, so let's talk about this analysis now. Let's say we've already accounted for the downshear propagation over here. We've addressed that previously. So this is already accounted for from the analysis. We're now going to look at the effects of what we'll refer to as the cross shear term, or effectively what's going on orthogonal to the deep shear vector, which is going to be associated with meridional shear profile over here. And so we're going to perform all of the analysis now along the y-axis rather than the x-axis, or along the axis that is orthogonal to the deep shear vector. So let's draw our Cartesian coordinate system, x, z, y into the page. Here's going to be our initial updraft over here, and we talked about with the deep shear vectors west to east and horizontal vorticity in the meridional direction. We'll have flanking updrafts to the right, to the left, or oriented along the y-axis over here. One over here to the right, one over here to the left. The one to the right, just want to specify real fast, since the horizontal vorticity is pointing from south to north using the right-hand rule, is that when we have this initial updraft, tilt that horizontal vorticity in the vertical, that'll be associated with positive value of zeta to the right, or mesocyclone, and then to the left, we'll have a meso-anticyclone, zeta being negative to the left over there. And now we'll consider a ground once again over here. And now let's perform the analysis of the effects of the vertical shear of the mean meridional wind associated with this term over here. And we're going to see what the alternating shear profile associated with the curved hodograph gives us. So let's do this for every single point relative to the individual flanks. So let's start out over here. We'll have down low relative to this flank, partial v bar, partial z, partial w prime, partial y. And we'll write that up here as well. In the high levels, partial v bar, partial z, partial w prime, partial y. We're going to do similar analysis up here. As we go towards this left member over here, partial v bar, partial z, partial w prime, partial y, and then down below, partial v bar, partial z, partial w prime, partial y. All right, so let's start out. We know that in the low levels, corresponding to that part of the hodograph, we will have v bar increasing in magnitude with height above the ground. We have more meridional flow from south to north component, so it's going to be associated with a positive value there and a positive value there. Now, in the high levels, effectively to the right of this dashed line, we'll have v bar decreasing with height above the ground. So as we get to the high levels, that'll be associated with a negative sign over here and a negative sign over here. Now, let's go toward each of those updrafts from the wings, effectively, of our analysis here, effectively starting out with no perturbation upward motion. And as we go along the y-axis toward our perturbation upward motion, that is going to be associated with, in both cases here, effectively above and below the updraft, a positive value of partial w prime partial y, a positive value of partial w prime partial y. And then as we go away as we go effectively to the north of, in this particular case, or away from this updraft mass, or multiple updrafts over here, that'll be associated with a partial w prime partial y that is negative as we go away from the perturbation updraft, and same thing over here. So previously, when we looked at partial w prime partial x, we were not dealing with alternating partial u bar partial z, so the analysis need only be performed at one level in the mid-levels where w prime is most substantial. But now we acknowledge that, that fact that w prime is incorporated into the spatial or horizontal changes in w prime. But the sign now, SIGN, of these terms is being more influenced by the fact that we have an alternating shear profile of the meridional wind associated with our curved bowed-out hodograph. So let's multiply things together. So in the low levels for the right flanking new updraft, we have net positive perturbation pressure over here, net negative aloft, and then for the left flanking member, or the meso-anticyclone, we have positive here, negative here, and the result is going to be upward motion to the right, downward motion to the left, and the result will be upward motion that is dynamically driven via linear processes associated with the perturbation pressure gradient force is going to be dominant upward for the right member over here relative to the deep shear vector, or also considered on the same side of the hodograph with concavity. This right member over here associated with a mesocyclone. And so that is the effect of the linear perturbation pressure term in terms of the background hodograph. The curved nature of that hodograph tells us something about which of the flanking cells is going to be dominant. The side of the initial updraft, where we have vertical motion maximized or upward motion maximized, is going to be the same as the side of the hodograph with concavity, as determined from the linear perturbation pressure terms over here. So let's summarize what's going on over here with this linear case. I'll just write some notes out here so you guys can get these down in your own notes. So for the linear term, the consistent shear sign, we'll just use this compound adjective over here, part of the hodograph, effectively looking down shear, tells us about the direction of downshear propagation. And it's the curvature in the hodograph that favors upward perturbation pressure gradient force for the same side of the initial updraft as the side of the hodograph with concavity. In this case, side of the hodograph with concavity relative to the deep shear vector is to the right. That is going to be associated with a dominant right mover. That is going to be associated with a mesocyclone. And in the case where we have the opposite flanking cell over here, that'll be associated with downward motion, and so that particular cell is suppressed. And we get the right flanking dominant storm for this particular case.